Join us on an hour-long journey across the stars. Relax, and let the universe tell you its story. Far away, a star 700 times bigger than the Sun is dying. Its final moments are unfolding right now. Betelgeuse burns in 6 million years. What our Sun will make in its entire life. But most people don't realize this red giant could explode into a supernova tomorrow, or 100,000 years from now. Hi everyone, I'm Youngshin. On the shoulder of Orion lies a star, bigger than Jupiter's entire orbit around the Sun. Its days are numbered. Betelgeuse has been burning for 10 million years, but now it faces a deadly crisis. Deep in its core, the nuclear furnace that powers it is starting to sputter, like a massive bonfire that's raged for millions of years. The fuel is almost gone. But the danger of Betelgeuse isn't just its size. If this red supergiant replaced our Sun, it would engulf Mercury, Venus, Earth, and even Mars. Its surface might stretch beyond the asteroid belt. Our entire solar system would fit inside it, like a tiny bubble. But the real threat comes when massive stars run out of fuel. Small stars fade gently into white dwarfs. But Betelgeuse is far too big to die quietly. Its death will be explosive. The moment nuclear fusion stops, gravity will crush its core in less than a second. The collapse happens so fast it's mind-blowing. The core shrinks smaller than Manhattan, yet it weighs more than our entire Sun. Then comes the rebound. All that crushed matter slams back outward at 30,000 meters per second, triggering a colossal explosion. For months, its brightness will outshine an entire galaxy. That's a supernova. When Betelgeuse goes supernova, we'll see it even in broad daylight. What worries astronomers is this red giant is already showing signs of instability. In 2019, its brightness suddenly dropped, leading some to think the explosion had begun, though it later brightened again. These changes prove the end is drawing near. The question is in asterisk if asterisk it will explode. It's asterisk when asterisk. This uncertainty comes from the strange timeline of stars. When astronomers say soon, they mean within 100,000 years, which, on a cosmic scale, is basically tomorrow. But for humans, that could mean dozens of generations away. We can't predict the exact moment. But we do know what comes after. It takes about 600 years for Betelgeuse's light to reach Earth. So, when it finally happens, for months the night sky will have to suns blazing overhead. Ancient cave paintings may have recorded past stellar explosions, a cosmic fireworks show that left a deep impression on our ancestors. This explosion will be breathtaking, and luckily, Betelgeuse is far enough away that deadly radiation won't harm life on Earth. We'll have front row seats, safe and sound, to one of the most spectacular events in the universe. That makes Betelgeuse unique among cosmic threats. Most don't wait for us to enjoy the view. They're just deadly, but this red giant has given us a countdown to the greatest fireworks show in human history. And yet, the real danger of stars isn't just their size. The deadliest stars in the Milky Way share one terrifying trait. They're massive enough to forge iron in their cores. Most people think bigger means more dangerous, but stellar physics works differently. Once a star is more than 8 times the mass of our Sun, it becomes a weapon of the cosmos. Its mass determines how it dies, and whether nearby planets are safe or doomed. Think of a star's mass like the pressure in a cooker. Small stars like our Sun can only fuse hydrogen and helium, creating gentle transformations that last for billions of years. After they die, they quietly expand, shedding their outer layers and turning into beautiful planetary nebulae, like candles slowly fading out in the cosmos. But massive stars are like nuclear reactors on the edge of meltdown. The crushing gravity at their core drives increasingly violent transformations. First, hydrogen fuses into helium, then helium into carbon and oxygen. As heavier elements are forged, temperatures soar to hundreds of millions of degrees, producing neon, magnesium, and silicon. Each new fusion stage demands more energy than the last. The star burns through fuel faster and faster, like a car with failed brakes racing downhill. A star 20 times the mass of the Sun burns hydrogen for 10 million years, helium for 1 million years, but carbon lasts just a single day. When the core starts producing iron, the real danger begins. Iron nuclei refuse to fuse into heavier elements because that process absorbs energy instead of releasing it. Iron builds up in the center of the star, like tossing wet logs into a furnace. The fire goes out instantly, with no fusion pushing outward. Gravity collapses the core in less than a second. The crushing force is so immense it fuses protons and electrons into neutrons. The released energy exceeds what our Sun will generate in 10 billion years. That blast rips through the outer layers, hurling them into space at 10% the speed of light. The explosion reaches 100 billion degrees, 6,000 times hotter than the Sun's core. Under such extreme conditions, this dying star creates elements found nowhere else in the universe. Gold, uranium, and more. Every heavy atom in your body was forged in the final seconds of a massive star's life. Distance decides whether a star's death is breathtaking or catastrophic. A supernova just 25 light-years away could strip Earth's ozone layer and trigger mass extinction, but the same blast 100 light-years away would just give us a dazzling light show with little damage. The most dangerous stars are the massive ones closest to Earth. Astronomers have found dozens of candidates within a range that could threaten our solar system. These cosmic ticking time bombs might explode tomorrow, or not for millions of years. We simply can't predict it. Even more unsettling is their sheer scale. To grasp how enormous these stars are, you have to let go of normal-size comparisons. If the Sun were the size of a basketball, the most dangerous stars in our galaxy would be bigger than a football stadium. When studying the largest stars in the universe, our sense of scale nearly breaks down. We need step-by-step comparisons to understand. So let's start with Earth. Earth's diameter is about 8,000 kilometers, which feels pretty big, but you could fit about 1 million Earths inside the Sun. The Sun's diameter is 864,000 kilometers, and light takes 4.5 seconds to cross it. That makes the Sun a fairly average star. Right in the middle of the size chart, like a bright yellow marble in the cosmic collection. Now imagine a star 50 times wider than that marble. That's Betelgeuse, a red supergiant. Here, the word big barely applies. If Betelgeuse replaced our Sun, Earth, Mars, and everything up to the asteroid belt would orbit inside it. Even the International Space Station would be flying within its atmosphere instead of outer space. The size of red supergiants is simply mind-blowing. Take VY Canis Majoris, for example. Its diameter is over 1 billion miles. Light takes 6 hours just to cross from one side to the other. A plane flying 500 miles per hour would need 2,000 years to circle it once. Maybe comparisons like that help it sink in. If Earth were a grain of sand, the Sun would be a giant ball. And the cluster itself, imagine a sphere taller than the Empire State Building. The size difference is so massive. You could fit about 7 billion suns inside this supergiant. These stars are so huge and powerful, you could see them from millions of miles away. The brightness of Canis Majoris, for example, equals 300,000 suns. If you swapped our sun for it, Earth's surface would instantly heat up to 3,000 degrees Fahrenheit, hot enough to melt copper. Stars this massive have mind-bending physical properties. Their outer atmospheres are barely held by gravity. Powerful stellar winds constantly blow material into space. These dying giants lose as much mass every few million years as the entire Earth weighs. But they're so huge that loss is basically nothing to them. Even more incredible, these stars live fast and die young. Our sun has enough fuel to last 10 billion years. But supergiants burn through it all in just 3 to 5 million years. That's less than 1,000th the lifespan of normal stars. The biggest stars we've found are wildly unstable. Their brightness pulses over months or years, as if they're breathing like a sleeping giant, expanding and contracting, and with every breath, the matter they move can span distances bigger than Jupiter's orbit. When these cosmic monsters finally die, they don't just explode. Their blast packs the punch of 10 billion hydrogen bombs going off every second. The death of a massive star unfolds in 3 devastating stages, each one more violent than anything humans have ever seen. Stage 1 begins just seconds before the collapse. Deep inside the star's dying core, iron atoms pile up like ash in a cosmic furnace. For millions of years, fusion has held the star against gravity. But iron changes everything. Instead of releasing energy, iron absorbs it, snuffing out the very fire that kept the star alive. With no outward push left, gravity takes over instantly, in less than a second. The core shrinks from Earth-sized to just 12 kilometers across. Picture this: crushing a basketball into a marble in a blink, while keeping all its mass. The density is so extreme. A teaspoon of this core would weigh as much as Mount Everest. And then, something even wilder happens. Protons and electrons get squeezed so tightly they merge into neutrons, releasing a flood of ghost-like particles called neutrinos. These neutrinos carry away 99% of the blast's energy, racing through the collapsing star at near light speed and into space. Stage 2 begins when the neutron-packed core reaches the point where it can't be compressed anymore. That triggers a shock wave that rebounds toward the surface at 18,000 kilometers per second, like slamming a rubber ball onto concrete. The core bounces back with incredible force, forming a wall of energy that rips through the star's outer layers. It takes hours for the shock wave to reach the surface, blasting through layers of silicon, oxygen, hydrogen, and more. In the process, it heats matter above 5 billion degrees, forging heavy elements like gold and uranium, all created in the star's final moments. Stage 3, the one we call a supernova, the spectacular finale. When the shockwave bursts through the surface, it blasts the outer layers into space at 6,000 kilometers per second. In just 10 seconds, the explosion releases more energy than our sun will produce in its entire 10 billion year life. Its light can outshine an entire galaxy of 100 billion stars. Yes, an entire galaxy. If a supernova went off, thus 25 light years away, it would shine as bright as the sun in our daytime sky, visible to the naked eye. And months later, it's expanding debris cloud. It cools, spreads out, and slowly fades. The aftermath of an explosion can create two strange cosmic objects. Stars with 8 to 25 times the sun's mass leave behind neutron stars. These city-sized spheres are insanely dense. Their surface gravity is 200 billion times stronger than Earth's. Even bigger stars collapse entirely into black holes, forming regions of gravity so strong, not even light can escape. The expanding shockwave doesn't just create heavy elements, it hurls them into space at astonishing speeds, seeding galaxies with the building blocks of worlds. A supernova, its shockwave ripples through space like an invisible tsunami, packing enough energy to reshape entire regions of a galaxy. When the explosion first bursts from a dying star's surface, it blasts out at 6,000 kilometers per second, fast enough to circle Earth in just 45 seconds. This balloon of superheated gas and magnetic fields doesn't slow down quickly. Even after thousands of years, the supernova remnant still races at hundreds of miles per second. That's its speed. The shockwave plows through the thin gas between stars, creating an ever-expanding bubble of destruction. Like a bomb going off underwater, the blast pushes everything around it outward. But in space, a supernova's blast sweeps aside cosmic gas and dust, heating it to millions of degrees, and hurling particles to extreme energies. These cosmic shockwaves can travel for hundreds of thousands of years before fading. The Cygnus supernova remnant spans 70 light-years across, and it's still expanding from an explosion 20,000 years ago. That bubble is big enough to hold 2,000 solar systems. How destructive the shockwave is depends on distance. Within 30 light-years of a supernova, the blast can strip away a planet's atmosphere and wipe out all life in its path. The radiation levels would be thousands of times what life on Earth can handle. Even at 50 light-years away, the danger is real, not as immediate, but enough to damage the ozone layer. That would let deadly ultraviolet rays reach the surface, wrecking the food chain, starting with plankton and plants, potentially causing mass extinction. Some scientists believe several mass extinctions in Earth's history may have been triggered by supernova blasts. At 100 light-years out, the shockwave is less of a threat to life. But more important for astronomy, it compresses clouds of gas and dust, triggering new stars to form. In other words, the death of a star can spark the birth of new ones. This cosmic cycle has repeated for billions of years. The shockwave also acts like a giant particle accelerator, launching protons and atomic nuclei to nearly light speed. These high-energy particles become cosmic rays, filling the galaxy and constantly raining down on Earth and other planets. When cosmic rays hit Earth's atmosphere, they trigger chain reactions that can even mess with computer memory or cause genetic mutations. The supernova remnants we see today record explosions from hundreds to hundreds of thousands of years ago. The beautiful Crab Nebula was first observed by Chinese astronomers in 1054. A supernova star, the Veil Nebula, comes from an even older blast in the 17th century. Even scarier, some stellar explosions produce focused beams of radiation, and they travel at light speed. The most violent explosions in the universe can fire deadly radiation billions of light-years away, like a cosmic laser cannon. These gamma-ray bursts are the extreme death throes of stars. The most massive stars collapse, not just exploding outward, but channeling their energy into narrow, focused jets, blasting through space at 99.9% the speed of light. Each beam carries more energy than our sun will produce in its entire lifetime. but it's concentrated into a beam, just a few degrees wide. Imagine it like a lighthouse beam, only instead of visible light. It's the universe's most powerful gamma rays. Each gamma ray photon packs so much punch. It can split atomic nuclei and even create particles out of the vacuum itself. Along with their antiparticles, when one of these death rays sweeps across a planet, the amount of radiation released equals 1 billion nuclear bombs going off, all at once. These jets form when a massive star spins rapidly and collapses into a black hole. Its rotation channels the blast energy along magnetic field lines, shooting to powerful beams out from its poles. These jets pierce through the dying star and race through space for thousands of years, gradually spreading out as they travel. Astronomers detect gamma ray bursts almost every day, but they happen in galaxies billions of light years away, far, far away. Yet even at those distances, the blasts still leave brief flashes on satellites here on Earth. They can last from just milliseconds to several minutes, and the energy output is staggering. A typical gamma ray burst, in just seconds, can outshine all the stars in its host galaxy combined. If a gamma ray burst went off in our Milky Way and pointed at Earth, the consequences would be devastating. In seconds, radiation would shred the ozone layer, leaving the surface exposed to deadly solar UV rays. The burst would also trigger chemical reactions in the air, producing nitrogen oxides that block sunlight, plunging Earth into an icy winter lasting years. Gamma ray bursts have a kill zone, far larger than a normal supernova. A regular stellar explosion is dangerous within about 25 light-years, but a gamma ray burst pointing at a planet can wipe out life up to 6,000 light-years away, a quarter of the way to the center of our galaxy. Thankfully, gamma ray bursts are rare, and their deadly beams are very narrow. Over the next billion years, Earth's odds of being hit are about 1 in a million. And even then, only the hemisphere facing the burst would take the hit. At first, the radiation might still allow some ocean life to survive afterwards. Some scientists even suggest that mass extinctions on Earth may have been triggered by gamma ray bursts around 450 million years ago. In the Ordovician extinction, 60% of marine species vanished. The timing and die-off patterns match what a gamma ray burst would be expected to do to Earth. These cosmic death rays remind us just how dangerous our galaxy can be, especially when some stellar monsters live so close to our solar system. Astronomers have even drawn a death sphere around the solar system, marking the distance where a stellar blast turns from beautiful to deadly, starting at about 25 light-years from Earth. Any supernova closer than that would release enough radiation to trigger mass extinctions here. Think of it as a cosmic no-fly zone, where dying stars pose a direct threat to life. Inside this range, an exploding star would be like being too close to a hydrogen bomb. Its energy would overwhelm Earth's natural defenses. No protection possible. On the inner edge of the danger zone, a supernova could raise Earth's radiation levels thousands of times above normal. Gamma rays and X-rays would rip apart the ozone layer in hours. Plankton in the ocean would die first, then plants on land, and eventually the animals that depend on them, until life collapses and complex species vanish. Between 25 and 50 light-years away, a supernova is less immediately lethal, but still dangerous long-term. Radiation could still weaken the ozone layer, raising cancer rates and disrupting ecosystems. Some species might survive, but Earth's biosphere could take millions of years to fully recover. Even if humans manage to endure, civilization itself could collapse. At 100 light-years away, a supernova is just a spectacular light show, with little to no effect on life. The radiation is too weak by then, and Earth's magnetic field and atmosphere absorb the rest. No catastrophic damage to ecosystems. Instead, these distant blasts create gorgeous nebulae and enrich space with heavy elements without threatening life. So far, surveys show there are 35 massive stars inside Earth's danger zone. Most of these ticking time bombs sit between 50 and 100 light-years away. Go close enough to worrying, but still far enough to avoid an immediate disaster. The nearest candidate is Ik Pegasi, about 150 light-years away. Not a serious threat for now. But what's more unsettling is, these danger zones drift around the galaxy over time. Our solar system races through space at 550,000 miles an hour. Orbiting the galaxy, it takes 230 million years to circle the Milky Way once. On this cosmic road trip, we pass through all kinds of regions, sometimes drifting near dangerous stars, sometimes moving away. 60 million years ago, in the age of dinosaurs, the solar system sat in a very different part of the galaxy. Some scientists suspect we may have been closer to an exploding star back then. It could have even triggered the mass extinction at the end of the Mesozoic. The evidence is thin, but the timing is suspiciously close to the event. Looking ahead, astronomers predict in the next few 100 million years, our solar system will run into several risky stellar neighborhoods. When we cross spiral arms of the galaxy, the odds of a nearby supernova go up. The risk never really goes away. It just rises and falls as we travel through space. But humans have actually witnessed stars explode close enough to see. Some were so bright they lit up the daytime sky. Throughout recorded history, massive stellar explosions happened close enough that our ancestors could read by their light at midnight. One of the most famous supernovae appeared in 1054. Chinese astronomers spotted it in Taurus, a brand new star, so bright it was visible in daylight for 23 days. At the same time, Native American rock art may have recorded this cosmic explosion, etched into cliffs in the American Southwest. What makes this ancient supernova so special is that we can still see its remains today. The Crab Nebula is visible through a small telescope. The expanding cloud of debris left from that medieval blast. At its heart spins a neutron star, rotating 30 times a second, like a cosmic lighthouse, beaming radiation into space. Records from China note that the 1054 supernova outshone Venus at first. For months, its brilliance was bright enough to cast shadows at night. After a year it faded away, but it forever changed how humanity viewed the heavens. Then in 1604, an even more spectacular explosion lit up the southern sky. Astronomers in Europe and Korea recorded the supernova in Sagittarius. It shone brighter than Jupiter, and at just 20,000 light-years away. It was practically next door in galactic terms. The 1604 supernova shattered the old belief that the heavens were unchanging and perfect. Religious leaders struggle to explain why God's eternal creation suddenly sprouted a brand new star. That explosion proved the universe is dynamic and evolving, helping spark the scientific revolution. Even earlier records describe stunning starbursts. In the year 185, Chinese astronomers documented a supernova that blazed for 8 months. Roman writers at the time noted an unusual star in Centaurus, though their records weren't nearly as precise as China's detailed observations. Perhaps the most intriguing was the 1006 supernova. It was seen by civilizations all over China, Japan, Korea, and Islamic astronomers across the Middle East. Even European monks wrote about the dazzling star, calling it a heavenly omen during times of turmoil. The brilliance of these ancient records lies in their accuracy. Modern astronomers point telescopes to the exact spots described in old texts and find supernova remnants whose ages match the written records, expanding shockwaves and glowing clouds of debris. The physical proof of what our ancestors saw. These historic supernovae erupted between 6,000 and 20,000 light-years from Earth. Far enough to be safe, but close enough to be spectacular. They showed early astronomers that stars are born and die. That discovery laid the foundation for our modern understanding of stellar evolution. Seeing this cosmic reality firsthand also reminds us that the Milky Way is still alive and dynamic. Massive stars continue to explode on a regular basis, one of the most beautiful stellar graveyards in our sky. Holds the secret of an explosion our ancestors actually witnessed nearly 1,000 years ago. Chinese astronomers saw a star explode so bright it was visible in daylight. Even now, centuries later, its expanding cloud of debris still glows with its dying light. The Crab Nebula stretches 11 light-years across and is still expanding at 900 kilometers per second. Think of it as a cosmic bubble made from the remains of a star 8 times heavier than our Sun. Every atom of oxygen, carbon, and heavier elements in this ghostly nebula was forged in the star's final moments. At its expanding heart lies one of the strangest objects in the universe. A neutron star only 12 kilometers wide, yet more massive than our entire Sun. This stellar remnant spins 30 times a second, faster than helicopter blades. Its magnetic field is 1 trillion times stronger than Earth's. It acts like a cosmic lighthouse, sweeping beams of radiation into space with every turn. When one of those beams points toward Earth, our radio telescopes pick up a perfectly timed pulse 30 times per second, so precise it rivals an atomic clock. Astronomers call it a pulsar, a cosmic timekeeper. What makes the Crab pulsar so special is its youth. Most pulsars are millions of years old, spinning much more slowly, but the Crab pulsar is less than 1,000 years old. Still in its energetic prime by human timescales, it radiates 100,000 times more energy than the Sun, powered by its leftover spin. Its pulsing radiation energizes the surrounding nebula, making it glow across the entire electromagnetic spectrum. From radio waves to visible light, X-rays, and gamma rays, every part of this stellar graveyard shines. Each wavelength reveals a different piece of the physics at work. Hubble's images show the Crab Nebula's structure is intricate, changing year by year. Clumps of gas race outward at thousands of miles per second. Magnetic fields twist into filaments stretching for light-years. The whole nebula looks like a cosmic jellyfish drifting through space, dragging glowing tendrils of superheated gas. The elements scattered in that ancient blast are now mixing with interstellar clouds, which will one day form new stars and planets. Every heavy atom in your body, the iron in your blood, the calcium in your bones, the oxygen you breathe, was born in the furnace of a star and scattered across the galaxy by explosions like this. Recent research shows the Crab Nebula emits gamma rays, more powerful than any other supernova remnant we've ever detected. These cosmic rays carry more energy than particles accelerated in our most powerful machines on Earth. In other words, the pulsar itself is a natural particle accelerator. On a galactic scale, this nebula is also a cosmic laboratory for studying physics under extreme conditions, magnetic fields, pressures, and temperatures that no earthly experiment could ever reach. It offers a whole new perspective on fundamental physics. Though the Crab Nebula is the remnant of a star we know exploded, other massive stars have tricked astronomers into thinking they were about to go supernova. In 1843, one such star in the southern sky briefly became the second brightest star visible from Earth. It's also a cosmic lab for studying physics under extreme conditions. The magnetic fields and temperatures here are impossible to recreate on Earth. giving us fresh insights into fundamental physics. While the Crab Nebula is the remnant of an exploding star seen in ancient times, other massive stars have tricked astronomers before, making them think a supernova was about to happen. In 1843, a star in the southern sky suddenly became the second brightest in the heavens. Astronomers thought they were witnessing a supernova. That star was Eta Carinae in the Carina constellation, about 7,500 light-years away. It's one of the most massive stellar systems we know. Its primary star is over 150 times the mass of our Sun. In fact, by standard physics, a star this big shouldn't even exist. It burns through fuel at a furious rate, losing the mass of an entire Sun every 1,000 years. The eruption in 1843 completely shocked astronomers. Within months, Eta Carinae's brightness increased over 10,000 times. It outshone every star except Sirius. In the southern hemisphere, people could see it even in daylight. Many thought they were witnessing a new star being born. But what they saw was something even stranger. A temper tantrum from a massive blue variable star. Eta Carinae didn't fully explode. Instead, it blasted off its outer layers in a violent eruption, throwing out material equal to 10 suns. This outburst created the huge lobes of gas and dust, still expanding today, at over 1 million miles per hour. Astronomers call it the Homunculus Nebula. From the side, it looks like a giant cosmic hourglass, about a light-year from end to end. The dust reflects light from the hidden star at the center. Images from the Hubble Space Telescope reveal astonishing details inside. Shockwaves, magnetic fields, and regions where fast gas slams into slower material. What makes Eta Carinae special is that it may show how the most massive stars behave. Just before their final explosion, the 1843 eruption released as much energy as a typical supernova. But instead of being destroyed, the star survived by shedding mass. This suggests that giant stars may undergo multiple eruptions before their ultimate death. Modern observations show Eta Carinae is actually a binary system. Two massive stars orbiting each other, completing a cycle every 5.5 years. The primary weighs in at about 150 suns, and the companion between 30 and 80 suns. When these two monsters swing close together, their stellar winds collide, creating fireworks visible across the entire electromagnetic spectrum. But the system is still unstable. Astronomers have detected smaller eruptions happening every few decades, suggesting the star could be on the brink of another major outburst. Some models predict Eta Carinae will go supernova within the next million years, which, in cosmic terms, is basically tomorrow. If Eta Carinae does explode, we'd see it on Earth even in the daytime, and at night, it might even cast shadows. The blast could also unleash a burst of gamma rays, but the chance of those deadly beams pointing at Earth is extremely low. This star system is just one example of a massive star. These kinds of stars can mimic their own death, tricking astronomers in the process. Back in 1843, Eta Carinae exploded, with more energy than some entire galaxies. Yet, unbelievably, this star survived its own catastrophic eruption. Observers in the southern hemisphere watched in awe, as a faint star suddenly became the second brightest object in the night sky. It brightened so quickly that astronomers first thought they were witnessing the birth of a new star, not the dying throes of an ancient giant. The physics behind this dramatic outburst defied everything scientists thought they knew about stellar behavior. Eta Carinae didn't collapse inward like a normal supernova. Instead, it blew itself apart from the inside. The core remained intact, while the outer layers blasted outward at over 1,000,000 miles per hour. Think of it like a pressure cooker with a broken safety valve. For millions of years, the star's nuclear fusion balanced perfectly against gravity's pull. But Eta Carinae grew too big and too hot. Radiation pressure began to overpower gravity's grip. When the balance finally broke, the star shook violently and hurled out material equal to 10 suns. That explosion created one of the most spectacular stellar debris fields ever seen. The blast carved out the famous Homunculus Nebula, which is still expanding at incredible speeds. High-resolution images reveal its intricate inner structure. Shock waves, magnetic fields, and zones where fast gas collides with slower-moving material. But perhaps most impressive is the sheer energy released. In just a few months, Eta Carinae unleashed as much energy as the Sun produces in 10 million years. The explosion was visible thousands of light-years away, briefly outshining its entire star cluster. This star managed it all by converting its own mass directly into energy. A staggering achievement. The eruption may have been triggered by runaway nuclear reactions in its outer layers, or perhaps instabilities caused by its rotation and magnetic fields. Some theories suggest Eta Carinae might actually be two giant stars in the process of merging. Modern research shows that this great eruption was just the biggest of several smaller outbursts. Astronomers have found evidence of earlier blasts dating back thousands of years. This suggests that Eta Carinae regularly sheds mass through violent eruptions. Each outburst strips away its outer layers, slowly reducing its total mass. Ironically, this mass loss may be saving Eta Carinae itself by blowing off its outer layers before collapse. It may be preventing the runaway chain reaction of a supernova. Instead of dying in one grand explosion, it's slowly tearing itself apart in stages. The remains of that eruption still today offer scientists priceless data. As the expanding shock waves crash into surrounding gas clouds, they light up material that was once invisible, revealing the structure of interstellar space surrounding star systems. But Eta Carinae is just one of many stars that fake their own death. These stars are masters of cosmic deception. In our galaxy, the most massive stars are playing a dangerous game of cosmic hide-and-seek. They vanish behind clouds of material they've ejected, only to shine brilliantly once again. Luminous blue variables are the most unstable and unpredictable stars in the universe. These giants can be 50 to 200 times the mass of our Sun, pushing the very limits of stellar physics. It's like driving too fast on a winding mountain road. A crash is almost inevitable. Their instability comes from incredible energy output. A typical luminous blue variable shines 1,000,000 times brighter than the Sun, with nuclear reactions so fierce they nearly rip the star apart. The explosive radiation pressure pushes outward with such force, it almost overcomes the star's own gravity. This creates a fragile balance that can tip in any direction without warning. Sometimes the star wins this tug of war, pulling its outer layers back. Other times, radiation pressure dominates, blasting huge amounts of material into space. These eruptions can make a star appear thousands of times brighter in just months or years. The most famous example is P Cygni. In 1560, it suddenly brightened to a third magnitude star. catching the eyes of European astronomers for the first time. It faded from view, then reappeared several times over the following decades, earning its mysterious nickname. What astronomers were really seeing was a massive star undergoing violent outbursts, each time ejecting material equal to several suns. That material temporarily hides the star behind its own debris, until it spreads out, and the star shines again through the expanding shell. Modern telescopes reveal that P Cygni is still surrounded by a tangled web of gas from centuries of eruptions. Luminous blue variables face one fundamental problem. They're simply too massive to sustain stable nuclear burning. The extreme temperatures and pressures needed to keep them going trigger runaway reactions that periodically tear the star apart. It's like trying to control a bomb factory, where more explosives are constantly being added. Many of these stars also spin incredibly fast, so close to the limit that centrifugal force could tear them apart. Their rapid rotation generates tangled magnetic fields, which can suddenly unleash stored energy in massive stellar flares. Some of these outbursts are like solar flares, but millions of times larger. On that scale, luminous blue variables become wildly unpredictable, making them especially dangerous neighbors. Unlike normal supergiants, which follow a predictable evolutionary path, these cosmic tricksters can explode without warning. During what seems like a routine flare-up, a star might look like it's just throwing off another flare, until its collapse suddenly accelerates past the tipping point. And then, astronomers in our galaxy have already identified dozens of candidates. Each one could be a supernova waiting to blow. And even more extreme than these unstable giants are stars so hot they're being destroyed by their own radiation. Deep in our galaxy, some stars burn at 200,000 degrees Fahrenheit, hot enough to vaporize anything we know instantly. Wolf-Rayet stars represent the final stage of evolution for the most massive stars. They've burned through their hydrogen and shed their outer layers, exposing the nuclear reactor core directly to space. What's left is essentially a naked stellar engine, running at full power, with no protective shell. These stellar monsters have surface temperatures above 50,000 degrees Celsius, 10 times hotter than the sun's surface. At these extreme temperatures, the star shines with a brilliant blue-white light, pouring out huge amounts of ultraviolet radiation. A Wolf-Rayet star's energy output can equal the power of 100,000 suns, all packed into a body only slightly larger than Earth's orbit. This intense heat drives incredibly strong stellar winds, blasting material away at up to 3,000 kilometers per second, like a cosmic hairdryer cranked to max power. The star is literally blowing itself apart with radiation. These stellar winds are so powerful that every 10,000 years, they can carry away mass equal to our entire sun. As the winds sweep outwards, they crash into surrounding gas clouds, creating stunning nebulae. The famous Ring Nebula in Aquila formed this way. Even though the Wolf-Rayet star at its center has since become a white dwarf, many Wolf-Rayet systems still show similar expanding bubble-like shells, racing outward at hundreds of miles per second. What makes these stars truly special is their chemistry. Their core reactions go far beyond simple hydrogen burning. Inside, Wolf-Rayet stars are fusing helium, carbon, oxygen, and even heavier elements. Their stellar winds carry these fusion products straight out into space, enriching nearby gas clouds with the elements needed to form planets. The extreme conditions inside Wolf-Rayet stars create some of the rarest elements in the universe. These stellar furnaces can forge fluorine and other exotic elements that only form under very specific temperatures and pressures. When the star finally explodes, it scatters this exotic matter across the galaxy. Most Wolf-Rayet stars are found in binary systems, orbiting a companion star that helps strip away their outer layers. The tug-of-war of gravity between them accelerates mass loss, exposing the Wolf-Rayet core even faster. In some pairs, mass regularly flows from the Wolf-Rayet star onto its companion. By cosmic standards, Wolf-Rayet stars live very short lives. They burn like blowtorches so intensely that in just a few 100,000 years, they run out of fuel, having already lost most of their mass. Through powerful winds, they usually end their lives in smaller supernovae, or collapse directly into black holes. Astronomers have cataloged over 600 Wolf-Rayet stars in our galaxy, each one a massive star in its final death throes. But when two of these stellar giants are locked in orbit together, the results can be catastrophic. When two heavyweight stars orbit closely enough, they begin a deadly gravitational dance that can only end in mutual destruction. Binary systems with two such giants create some of the most violent, spectacular events in the cosmos. As they orbit, these stellar partners lose energy through gravitational waves, causing their orbits to slowly decay. The stars spiral closer in a deadly embrace, accelerating into a fatal death spiral. Think of it like two figure skaters spinning, faster and faster as they pull each other in. Except these cosmic dancers weigh millions of times more than our sun. Their final embrace unleashes more energy than an entire galaxy. This process may take millions of years to unfold, but the final moments happen with devastating speed. In the early stages of orbital decay, the stars begin to tidally distort each other. Immense gravity stretches and squeezes them, raising bulges that point directly at one another. Material from the outer layer starts flowing between the stars, forming streams of superheated gas spiraling inward at high speeds. As the orbit continues to shrink, their stellar winds begin to collide. The collision zone produces shockwaves, heating gas to millions of degrees and accelerating particles to near light speed. The resulting radiation can be detected across the entire spectrum, from radio waves all the way up to gamma rays. One of the most spectacular outcomes of binary evolution, the radiation produced can be detected everywhere across the electromagnetic spectrum, from radio waves all the way to gamma rays. One of the most dramatic binary star events happens when one star goes supernova, while its companion survives. In just seconds, the explosion blasts away about half the system's total mass. That suddenly weakens the gravitational pull holding the orbit together. The surviving star gets flung out at over 600 kilometers per second, ejected from the system. That's fast enough to escape the Milky Way entirely. As these runaway stars speed through space, they plow up shockwaves and bow-shaped ripples through interstellar gas. Astronomers have already discovered dozens of these stellar refugees. Their extreme speeds and unusual chemistry reveal their violent origins. Some runaway stars even show clear contamination from their exploded companions. When both stars in a binary system are massive enough to go supernova, things get even stranger. The timing of a double supernova depends on the star's masses and orbital setup. If both explode within a few million years, the second blast erupts right inside the cavity, carved out by the first supernova shockwave. Some binaries manage to avoid instant destruction, but still can't escape their fate. If both stars collapse into neutron stars, or black holes, dense, compact objects, they'll keep spiraling inward, emitting gravitational waves. In their final moments of merging, they unleash some of the most powerful bursts of energy in the universe, briefly outshining entire clusters of galaxies. When two neutron stars collide, their gravitational waves are strong enough to be detected on Earth. They also produce intense gamma-ray bursts and forge heavy elements through rapid neutron capture, things like gold and platinum. These binary mergers are just one kind of cosmic explosion astronomers use to study the fundamental nature of the universe. In distant galaxies, dying white dwarfs explode with a precise and powerful energy release. Astronomers use them as cosmic beacons to map the universe's expansion. Type A supernovae come from white dwarfs in binary systems. The white dwarf siphons matter from its partner, and when it reaches 1.4 times the sun's mass, a runaway explosion ignites, completely destroying the star. Because the energy release is so consistent, they serve as standard candles for measuring cosmic distances. They helped reveal the accelerating expansion of the universe and dark energy. They're also the main source of iron in the cosmos. A single type A can create more iron than the sun's entire mass. Massive stars, though, meet an even more violent end. As their cores fill with iron, fusion stops, and gravity causes a catastrophic collapse. In just half a second, the core shrinks from 8,000 kilometers across to only 50. Electrons and protons combine into neutrons. 1 second later, it shrinks again to just 12 kilometers wide. The core rebounds, sending out a shockwave. Neutrinos flood energy into it, blasting through the star's surface. Within 8 to 15 seconds, the outer layers are hurled away at 10% the speed of light. A supernova is born, and in the process, gold is forged through rapid neutron capture. All heavy elements trace back to this. Every heavy atom we know comes from here. Neutron stars are insanely dense. Their surface gravity is 200 billion times that of Earth. Their crust is harder than diamond. Inside, scientists believe bizarre spaghetti-like structures may exist. When combined with rapid spin and powerful magnetic fields, they become pulsars, so precise, they rival atomic clocks. When two neutron stars collide, they unleash gravitational waves, and bursts of gamma rays, forging heavy elements. If the mass exceeds 0.5 times the sun's, the collapsed core can transform into a black hole. Beyond the event horizon, escape is impossible. At the singularity, physics itself breaks down. These stellar black holes range from 3 to 100 times the sun's mass. Astronomers observe them indirectly through radiation from their accretion disks. Supernovae act as cosmic nurseries. Their shockwaves compress clouds of gas, igniting the birth of new stars. The Orion Nebula was born this way. Even our solar system may have been sparked by a nearby supernova. Stellar fusion follows what's called the iron peak rule. Fusion stops at iron. Heavier elements than iron can only be created in supernovae or neutron star mergers. Every heavy element in our bodies comes from exploding stars. Red supergiants represent the upper size limit of stars. They can stretch over 1 billion miles wide, but their lifespans last only a few million years. They end in spectacular supernova explosions. Astronomers track these massive stars using tools like spectral analysis and brightness monitoring. Robotic telescopes, along with gravitational wave detectors, form global networks. They discover hundreds of exoplanets each year, helping us piece together the life cycles of stars and their role in shaping the universe.